infinite time under the mean curvature flow. So I want to sort of discuss like singularity formation of the mean curvature flow. Right, and so if we remember, which we should because I just said it, but basically if you have a flow, sigma t, defined maybe, this becomes singular at t, precisely when the limit as t increases to t of the sup over sigma t of the second fundamental form becomes infinite. So if the curvature blows up, I just want to remark that very recently Haizhang Li and Bing Wang showed, at least when the ambient dimension is 3, that in fact you can refine this a little bit and say, in fact, the mean curvature blows up. And I think they claim they could do it in higher dimensions, but that hasn't been solved. So that's still an open question of whether the mean curvature blows up at the first singular time. Okay, so that being said, I mean, this is pretty coarse information about how the singularity forms, so we want maybe more precise information about what singularities look like. So we want And one of the things that sort of this suggests to us, and certainly has been exploited in earlier work, is that the curvature, if you sort of dilate a surface, scales by sort of 1 over the dilation factor. So if the curvature is blowing up, it kind of makes sense to try and zoom in on the flow. And again, we would use this parabolic dilation of the space-time track. Maybe you can zoom in so the curvature becomes bounded and then pass some limit, and then you would get something that would at least presumably model the singularity, but would be kind of well-behaved, non-singular. So that, of course, is a standard procedure in geometric analysis. And in general, the idea is, of course, to maybe like do a blow-up, say maybe on the scale of curvature, and sort of study the resulting limits. So this is sort of a very general idea that has been applied to many different problems. But of course, the problem is, what do you get in the limit? So the limit may just be some new flow that, maybe the most you can say about it is because you've zoomed in parabolically, the interval of existence becomes sort of negative in the past, so it's an ancient solution. But maybe all you can say about it is that it's an ancient solution, and there's, in principle, many of those. So in Ricci flow, there's, at least in low dimensions, that's pretty well, and there's good classifications of such solutions, but in mean curvature flow, that seems kind of hopeless. And nevertheless, you would maybe expect that if you do this a little more precisely, you get even more of a special solution. And that is, in fact, the case. So we have this very powerful tool, which is called the Huysken Monotonicity Formula, which I'll get to hopefully soon. So this is actually going to tell us many different things, but one of the things it will tell us is that this sort of blow-up analysis always, at least if you do it correctly, produces a sort of special dilation invariant models of singularities. All right, so in other words, if you do this zooming in procedure, instead of just getting an ancient solution, you actually get a dilation invariant solution, sort of the shrinking sphere being the prototypical example. Okay, so I want to get to that today, but let me maybe, before I do that, just mention a few other related concepts. Okay, so before I get to this monotonicity of this Huysken type quantity, I want to talk about just briefly mention this area monotonicity. Okay, so this is actually a very elementary. This is sort of a very. These are very elementary. Or this is sort of. This is coming from. This is all going to come from the first variation formula. Okay, so the first observation is suppose we have, say, a mean curvature flow of closed hypersurfaces. Then the first variation formula tells us that the change of the volume of sigma t right, is going to be the integral over sigma t with a minus sign of the norm of the second fundamental form squared. This is precisely, as I said, the fact that the mean curvature flow is a negative gradient flow of area. And of course, this is, because we're closed, the mean curvature can't identically vanish, so this is actually strictly decreasing. And in fact, you can, if you want, you can even be more precise in many situations. So that tells us, of course, the volume of a closed guy is monotonically decreasing, and this is very useful and obvious. But in fact, one of the very interesting things about the mean curvature flow is actually sometimes you can kind of localize this monotonicity by using cutoff functions, and that's actually, as I said, there's this other notion of weak solution that has to do with the measure theory, and it's related to the formula I'm about to write. So we can actually localize this in monotonicity in space-time. Okay. So let me say, rather than, of course, once we have this differential inequality, we can integrate it and get an integral inequality involving how the area decreases. So it's easier to state this localized formula in this integrated sense. So what we get is that if, again, for any mean curvature flow, let's now assume it's from, I don't know, T naught minus. So R is some radius. Then what we see is that actually the area of sigma at this time t naught is out of the ball of radius r over 2 around some point p naught. Right. So here's the localizing the area. This is actually bounded in terms of some factor that 8 that comes from the proof, times the area of sigma at a previous time that depends parabolically on the radius. So, okay. Okay, so just a geometric picture, pictorially, what do we have? We have, here's our Here's our ball. Here's our P naught. Here's our R over 2. We're going to go back a parabolic amount. So this is time T naught. This is time T naught minus R squared over 8n. And we take a bigger ball. Okay, so the amount of area of this mean curvature flow, we don't say anything, we don't care about what's happening outside of this localization at all, is controlled by the amount of area in here. So for instance, if we have a reasonable amount of area here, we can't suddenly have like lots of sheets in here. Like that's not allowed because that would make the area go up, which bigger than this factor 8. Okay, so this is a very important property and a very important kind of localization property of the mean curvature flow. Okay, so the way this is proved is basically, it's essentially this first variation formula, but instead of doing the whole surface, which we can't necessarily do because we're not even assuming closed anymore, we introduce a cutoff. So I don't want to go over that maybe in the interest of time because I don't think it's that enlightening, but let me just mention what the formula is. So a consequence of the, again, the first variation formula is that phi is a, say, C2 function of compact support on space-time. Then we can look at the, say, evolution of the integral over the cutoff time t, and that turns out to be given by and we're integrating against the volume form, but I ran out of room. Okay, and the important point about this is, of course, this Laplacian, because it's compactly supported, we actually disintegrates by parts. This is actually, I'm just adding this in here to see that we, for example, if you choose a phi that has maybe it's like a sub-solution of the heat equation, then we get a good sign. But we could actually get rid of this or replace it with other terms, like it could be plus or minus. It doesn't matter. This ddt, if you recall, this was a special vector field. So, of course, ddt of phi is the ambient spatial derivative plus the mean curvature vector dotted with the ambient gradient of phi. Okay? So the point is, to prove this, we just choose a reasonable cutoff function. And the basic idea is your basic cutoff that you're using in all of these types of things is a kind of cutoff that's modeled on a sort of shrinking sphere. So if you let psi be 2nt I think plus. Okay. So if you work it out, this applied to such a psi, this is actually an exact solution. So what you do is, of course, that's not compactly supported, so you have to, do your standard thing of, taking the positive part of it and taking a high power to make it regular enough. But so there's some work to be done there, but maybe in the interest of time, I'll skip that. Right. So the point is, and you can check this. It's a good computation. It should be the case that ddt minus. I might have a sign wrong. I'm always bad about this. Is 0. Okay, so this is the basic cutoff. You're going to the basic ingredient in the cutoff to prove a result like this. Okay, so that's area monotonicity, and again, this is a very important result. And this integrated version, you integrate this up, you can think of this as a kind of basis of how you might start defining a notion of weak mean curvature flow where you think of the surface in terms of a measure. So that's the so-called notion of rocky flow. Comes out of this formula. But let me now move to this Huysken monotonicity formula. Okay, and the basic idea in the Huysken monotonicity is we're going to pick another very reasonable function on the ambient space-time, which has to do with the essentially the heat kernel in Euclidean space, or at least the backwards heat kernel, again with a slight modification to make it compatible with codimension 1 mean curvature flow. So the idea is let's consider, again, space-time negative. So this is space-time with negative times. So on this, we're going to let this function capital phi of the okay. So again, t is negative, so this is positive, so this thing decays exponentially fast, and then we have this negative power, and here the dimension is n, and this is going to be our basic formula, and we're going to, again, by translation, we'll sometimes want to change the, right, this becomes singular, in a sense, as time approaches 0 at the spatial point 0. We're going to want to shift that around, so we're going to let this guy be the shifted guy. So this becomes singular at the space-time point x0, t0. Right, and the observation is that this is essentially the backwards heat kernel on this space up to a dimension shift. So here, to really be the backwards heat kernel, we would want this to be n plus 1. So the point is if we let phi hat be equal to this guy is the backwards heat kernel. So specifically, it means that the backwards and the okay, so we have this backwards heat kernel, and we're going to see that it turns out that if we plug this kind of function into a modification of the first variation formula, then we're going to get a very nice monotonicity formula that has the right behavior under parabolic dilation. Right, so the point is, if we go back here, of course, if we think of this is, of course, dilation. I mean, this is a dilation invariant inequality once you read through it, but it doesn't really tell you anything about the ratios. It just tells you about the mass itself. So it's not going to be good for doing a blow-up analysis. Okay, so what is the monotonicity formula? basically, if sigma t is a mean curvature flow with sort of, and I don't want to get into this, but with reasonable volume growth. So for example, if it's closed, we can drop this hypothesis. But basically, anything you can imagine satisfies this. Then for any t in I, t less than t naught, if we compute the rate of change of the integral over sigma t of the function phi of then that's equal to minus the integral over sigma t of which of course is a non-positive number. Okay, so basically the integral of the mean curvature flow, when you pair it with this backward sort of modification of the backwards heat kernel, is not increasing under the flow. Okay. And the proof of this is, as I said, essentially from this first variation formula. Together with, I mean, it's in the end, this is sort of the key fact once you do all the manipulations. But the key fact is that if you take the ambient Hessian, Euclidean Hessian of the log of let's just think, I mean, again, going back to the symmetries of the problem, which if you think about it, you can certainly reduce this to the case that the x naught and t naught is the origin, space-time origin, because of the, again, you have to think about it, but because of the space-time translation invariance of mean curvature flow. So let's consider just the case. So the key computation, in some sense, comes down to the fact that the log of phi, when you take the Hessian, has a certain convexity property, or in this case has an exact equality. So it's, if you add times the Euclidean metric, then this is equal to 0. And in fact, the key thing in the end is that it's actually, I believe, positive. If I have my sign correct. Okay, so in fact, you could get a monotonicity formula as long as you have that this 2 tensor is non-negative. Again, I might have the sign wrong, because I'm bad with that. But in our case, it's actually 0. Okay, so what is the region for that? Well, let's just, again, do the computation. So if you integrate over right. Then by this formula, well, we're not going to use as I said, this Laplacian part is basically integration by parts. You can put anything in there. And again, this is where this growth hypothesis comes in. Because this rapidly decays, we can actually put in okay. And the point is we want to shift from sigma t from the intrinsic Laplacian to the extrinsic Laplacian. But again, this is it's a standard fact that the extrinsic Laplacian of phi is equal to the intrinsic Laplacian of phi But we have to add the Hessian of phi evaluated in the normal direction, right? There's one extra second derivative in the normal direction, and then there's a mean curvature term, so it's plus the mean curvature vector. Do I have that right? Minus the mean curvature vector. Minus the mean curvature vector. Okay. Okay, so we can replace this intrinsic Laplacian with the extrinsic Laplacian. So the point is, if we do this, this is integral of sigma t of d dt. And of course, the d dt is really the del t plus the extrinsic Laplacian of phi plus, right, so the Laplacian sigma t, so we have to, we want to subtract it, so we need to add it, so we get plus 2, okay, and so now this of course is should be the gradient should be x perp over minus 2t, with a minus sign. Okay, so we're going to combine, right, so this should be right, so what that should tell us is we're going to get the integral over sigma t of we're going to add and subtract this is x perp phi. Oh, and I forgot the Hessian of phi. Okay. Right, but if we think about it, remember this phi differs by the phi hat, where this would be 0 by a factor of basically a factor of multiplying by a factor of t essentially. So if we use that, we're going to end up with basically putting the phi hat in there and working it out. We should get a phi over minus 2t. And we can combine this by putting, remember there's a phi here, but if we think about how this relates to the log, we can combine these two terms, and this should be a phi, if I did this correctly, a Hessian of log of phi evaluated in the normal direction. But the point is, if we look at this, the Hessian of with a minus there is a plus of this, and the normal is unit length. So we get a minus 1 over minus 2t times phi, which is exactly, I guess this thing has a phi here. Right, these two terms exactly cancel. And if you have the inequality, this should have the correct sign. Right, so you get that this is really equal to what we wanted. This, of course, is less than or equal to 0. Okay, so that's the proof of this Houston monotonicity formula. Okay, so the key, again, when you have a question, when you have an inequality like this, of course, the natural question is to ask what happens about when you have equality. Well, that's clear is that you have equality, again, let's just suppose we're at this special case of you have equality if and only if the mean curvature of sigma t plus the normal part of the position vector over minus 2t is equal to 0, identically. So before, I mean, we can say something about this, but let me actually change gears a little bit and try and understand how we might think about this differently. So the observation is basically, as I said, if you think about how things scale in phi, if you parabolically scale the problem, then that's the same. That basically scales like minus the dimension. Right, because the x squared and the t cancel, and then you just get the factor from the minus n over 2. So the point about this is that if you have any gamma, n-dimensional gamma inside of Rn, and you integrate, say, gamma against phi at t, right, that's the same as integrating when you scale gamma by a factor rho, phi, and right, because the point is you're basically plugging in rho times rho squared. You're basically using this formula to get the rho to the minus n, but of course the volume form related to this is rho to the n, and the two things cancel. Right? That's why we had to change the power in terms of t to make everything scale correctly. So, in other words, this as long as you change the time in the appropriate manner, this integral is dilation invariant. And so, what the monotonicity formula is telling you is that if you have a mean curvature flow that moves just by scaling, then you should have a constant for this integral, and hence should satisfy that equation. And the point is that's really what happens even in the converse direction. So, right, so the observation, right, is if right. The point is the integral over the square root of minus t gamma of phi right. This, of course, is, as we said, is the integral over gamma of phi of is a constant in t. Right, so if you have a dilation invariant flow, by the monotonicity formula, you see that, and you can see this more directly, but I just want to do it this way. This implies that the mean curvature of right? Which, of course, if you just take t equal minus 1 for all t, okay, so this is a very special elliptic type equation. So it's elliptic because it's a prescribed mean curvature. We're saying the mean curvature is minus the normal part of the position vector divided by 2. And this is called the Self-Shrinker equation. And a surface gamma that satisfies it is called a self-shrinker. And so what this computation tells us is if we have and it's called this because if we have a solution that shrinks by mean curvature flow, then it has to satisfy this equation. Conversely, and this is a little bit, again, this you actually just plug it into the formula, and you can see if you take a solution to this, and you form this family of surfaces, you can check that is actually a solution to the mean curvature flow, right? So the reason is, of course, well, I'll leave that as an exercise. So you can check the converse. So conversely, the converse is true. It's also true. Okay, so in other words, the self-shrinkers, the flows they generate are precisely the only situation where you have equality in the Houston monotonicity formula. Okay, so now what's the last step of what I wanted to talk about? Well, how am I doing on time? How much longer? Was it 10 minutes? 10. All right, let me just finish by just giving some examples of these self-shrinkers, and then I wanted to start talking about another topic related to this, but I'll do that on the next talk. Okay, so let me just end with some examples that show that we actually have a lot of these self-shrinkers. And again, these are the mean curvature flow analog of the shrinking gradient Ricci solitons. But okay, so what are these? Okay. Okay, so the trivial example is the plane Rn. This is a plane through the origin. So of course the position vector there is always perpendicular to the normal component, so the normal component of the position vector is 0, and the mean curvature is obviously 0, so that's easy to see. Another one which we already saw is the sphere of radius 2n, so the round sphere. So again, that's a straightforward, we already saw this example, or it's an easy computation. We can, of course, form sort of products. So there's these round cylinders. Okay. So these are somehow, as we'll see, hopefully later, these are somehow these are the standard examples. So these guys are somehow the generic examples, which we'll see again and again. There's more exotic ones, which are, some of them are rigorous. So there's the so-called ongenate torus. Right, so these make sense in any Rn plus 1. This is in R3, though there's generalizations to higher dimensions. So roughly speaking, it's a torus of revolution. So it doesn't have an explicit formula. You have to solve an ODE, but it's so you take a torus and rotate it. So there's some profile curve which satisfies an ODE. The reason this is useful is, of course, this is compact and not the sphere. But when I talked about the net pinch, you could pick this guy to pick the neck to go through the center, and then this would shrink down and cut the neck. If you make the size of the neck small enough, you can make this shrink before the sphere shrinks. And another interesting family of examples is due to Capuleus, Klein, and Moeller. So this is again in R3. These are some non-compact So the idea here is you take the round sphere, so S2, this is, and you take the plane through the origin. So you kind of look at the union of these two guys, right? So you can think of this as like a singular self-shrinker. So there's a sphere and a plane, and they intersect. So at the intersection point, it's singular. But then what they're able to do is they're able to desingularize this. So it's very hard for me to draw, but they cut out a neighborhood of the intersection and kind of glue in little handles that are modeled on so-called Schurk surfaces. So they cut out the intersection and glue in little handles, which are able to perturb all of this to still be a solution. But in order to perturb it, it's interesting. So at infinity, instead of being flat, they have to it's a conical, but it has a kind of wavy behavior. So I'm not doing this justice, but basically at infinity, it looks like a cone, and the link of the cone is sort of wavy, so it has positive and negative curvature. And as you come in, there's some handles and some inside part, and then there's these two spherical caps. So these have been rigorously constructed using sort of gluing methods. And then there's a lot more numerical examples and some rigorous examples, but there's a lot of interesting questions in producing new examples. So one question you could take is if you could take two planes and kind of put a bunch of handles between them, it would sort of double two planes. Whether such a thing can be rigorously constructed is an open question. Okay, and then the final remark before I end is if we think about these, looking at the associated flow, the associated flow of this guy goes up to time 0 and just stops as a plane. But you could, of course, restart that as a smooth flow and just continue it as a smooth, flat plane. So this is sort of a regular shrinker. But all these other guys, as you run to time 0, they all become singular. And it's sort of impossible. And I mean, these guys, they disappear at time 0, and this guy disappears at time 0. This guy becomes the asymptotic cone at time 0. You could maybe restart it, but you would have to kind of form, no matter what you did, there was a singularity at time 0. So what turns out to happen is when you combine that observation with this Huysken monotonicity formula, you can see that for any mean curvature flow, if you do a kind of blow-up procedure at a singularity, you're going to get one of these shrinking examples, and it's going to be not this flat one. It's going to be one of these other ones. So these basically are the singularity models, which you can prove that precisely with the monotonicity formula. So I'll talk about that next time, but I'll stop here.